So we've talked before about how we have definitive proof that astronomers have not secretly discovered aliens, right?
Yeah, I mean, if they had, astronomers would have announced it immediately. There's no deep state government conspiracy keeping any astronomer quiet. That's just not the way that those people work.
In fact, just a few months ago, we heard about the kilonova discovery, which was a secret until it wasn't.
Yeah, there was a tweet about that from my old boss, and yeah, you can learn more about that on one of our previous episodes of Three Body Problems with Yair Arkavi. But yeah, some of these big announcements are a bit premature, or people kind of get pushed into announcing results that maybe aren't quite confirmed or not ready for prime time yet. And so we have an expert on this topic and other astronomical topics with us today, Professor Brian Keating from UC San Diego. So welcome, Brian.
Thank you. Now I understand I was set up. Okay.
Okay, so your area of research focuses on the cosmic microwave background, the CMB. So can you give us just a quick overview, a quick couple sentences about what is that?
Yeah, the cosmic microwave background is really the oldest light in the universe. It's the heat left over from the formation of the elements. And when elements are fused, they are likely to break apart when the temperature of the universe was higher than about, a frosty 10 million or so degrees. And once the universe dropped below that temperature, then the nuclei could remain stable, but the heat and the photons endure forever. And these photons travel throughout the universe, and as the universe cooled off and expanded, they've redshifted and their energy is reduced dramatically, such that they've gone from tens of millions of Kelvin down to a truly frosty 3 degrees above absolute zero. And this is the cosmic microwave background radiation. It's a radiation of photons that comes in all directions.
And so when you're observing the CMB, what is it that you can learn about the conditions in the early universe?
The other things that these photons can do is determine the properties of space-time itself.
Yeah, so that's some of the most cutting edge observations. The CMB observations, it goes back to the 60s, right? And the theory behind it. But really the cutting edge stuff that your group and others are working on are trying to see how gravity, how the entire history of the universe, so the very first, micro, tiny fractions of a second, can affect this light that we can then see today. And so that led to what we were sort of starting to hint at the beginning of this episode of some very big splashy announcements that turned out to maybe not be exactly what the people thought it was who were making the announcement. So what happened there exactly?
So we had been, searching for this signal that could potentially reveal the presence of gravitational waves written on the cosmic microwave background radiation. And if we detected this pattern, which is called B-mode polarization, that this pattern would be indicative of the existence of not only a background of photons, but a background of other massless particles called gravitons or gravitational waves. So we designed and built with colleagues at Caltech and Harvard and Minnesota and Stanford and other places around the world. We built an instrument that we deployed to the South Pole, and it was called BICEP, and we later upgraded it, and we called it very creatively BICEP 2. And that the reason that we called it, I came up with the name BICEP, kind of I'm an unrepentant punster, and BICEP stood for Background Imager of Cosmic Extragalactic Polarization, but also it was a hint to the notion that these patterns we were looking for, twisty, swirling patterns or curls. And, my friends who actually go to the gym tell me that the bicep is the muscle behind curling at the gym. So I wanted to muscle my way back to the beginning of time, and the bicep instrument became that device. And it was really a simple telescope. It's a Galilean refracting telescope with 2 lenses that are not transparent to visible light, but transparent to microwave light. And we stared at the microwave background from the South Pole for 3 years with BICEP 1 and then 3 years with BICEP 2. And then in 2014, we made the announcement that we had detected these waves of gravity. Now, what's so interesting about this detection is that the only mechanism cosmologists thought could produce a truly cosmological primordial background of these waves would be the so-called theory of inflation, which is an epoch of ultra-rapid, some say superluminal expansion of the size of space that seems to be required, or some form of it, to explain the properties of the universe that we see today. Namely, the universe is flat, the universe is incredibly large and very similar on scales, and it has tiny imperfections. And where those tiny imperfections are thought to originate from is called inflation. If the Big Bang had a sort of a gunshot, then the gravitational waves would be sort of the smoke from the gun. So finding the gravitational waves meant we would have a direct evidence for inflation. And so we announced on St. Patrick's Day 2014, not after imbibing beverages that you guys are so fond of, but in reality, we actually announced this discovery that we had detected these B modes, these curl modes, this pattern of twisting microwaves that would indicate the universe began in an inflationary epoch. And we became the toast of the world, and we were featured on the front page of every newspaper and magazine around the world for a period of time. And later on, things got really interesting.
I remember seeing an exhibit on this at the Science Museum in London, so that was all put together really quickly. It was that exciting. What went wrong?
So what we neglected to accurately account for is a secondary source of the signal that we saw. And yet we did know that inside our galaxy there is a substance which is called dust, which is very familiar to those of us who have small children. And the dust produced in the explosion of stars called type 2 supernovae can be really traced to a chemical, mineralogical, and elemental composition that has a lot of elements contributions that are magnetic. And these tiny grains of dust can act like little compass needles, and they can indeed get aligned by the Milky Way's magnetic field. The Milky Way has a weak magnetic field, and that magnetic field can orient the needles of dust just like on Earth, the Earth's magnetic field orients the needles of a compass. While we did know that was a possibility, we had no direct data that provided a measurement of how big that signal would be. So what we had to do is use computer modeling and theoretical assessment of how big that signal would be. We knew that there was a map of the dust that would have eliminated any doubt whatsoever as to the origin of the signal that we saw. And so that unfortunately was possessed by an arch rival and competitor of ours, namely the €1 billion Planck satellite. They had been measuring for as long as we had been measuring with BICEP2, and they had claimed that they had the sensitivity to make this measurement and do so better than us, faster than us, not cheaper than us, but nevertheless scoop us. And the history of cosmology is written by the winners, the ones that make the discovery first, and then they get their names in history and get to wear gold medallions around their necks. And so we were in a fierce competition with them, or so we thought. And although we asked nicely for access to their data, they didn't provide it to us. So instead, we actually found that someone from their team had actually published the data online. It wasn't refereed, it wasn't peer-reviewed, it had a lot of caveats on it. But nevertheless, we took that data, we turned it, from a kind of a throwaway image in a talk into a core argument for one of the models that helped us assuage our fears that we had seen dust. And so once we were confident that we had not seen dust, then we went ahead with the announcement several weeks or months later.
But I think, and I'm curious your opinion, but, it seemed like if you had published a paper and you came out with it and it was picked up and people thought it was interesting and then found out later, there was something that wasn't quite right in the analysis or something not quite corrected for, okay, and then the team goes back and maybe writes, a new paper with new data, and that's sort of the process of science. But at least, sitting on the sidelines of this kind of work, it seemed to me that making that big announcement and, saying that this is the first time we saw this thing, like that big, I don't want to call it a PR stunt, but it was a big PR splash, was what made this such a, pushing it to such an important in the media kind of idea made kind of the fall or the fixing of it so drastic.
Well, peer review wouldn't have really changed anything because the eventual paper was peer reviewed. It had the same conclusions in it. It was just couched in a lot more kind of hedging a little bit as to the ultimate interpretation, or if sentences in it. Now, I think the ultimate, I wasn't involved with the decision to have either one of those events, but it did turn it sort of into a spectacle. And I argue in the book that I think a lot of that is driven by this need to have scientific breakthroughs be, the biggest discovery of all time, and the greatest, most spectacular breakthrough, and in particular in cosmology. But the question of, I think it's really driven by, ultimately the Nobel Prize plays a big role in it, in my opinion, and that was certainly something that we considered, and that happens a lot. I always like to point out that you see a lot of press conferences and press releases and front page articles, but you never ever see like a front page retraction in the New York Times. And I think we should have that.
But I think one thing that the public don't necessarily get is that it doesn't discredit science, really. This is how science is done. We're trying from our one little rock in one corner of a galaxy to figure out what happened in the very early universe. And there are so many assumptions and models and things that go into doing something like that. And you do your best and you get it wrong and you figure out why it's wrong and try it again. And that's kind of how science works.
Absolutely. Yeah, I speak about that in the book. I actually call the Earth a mote of dust, and it is. It's a giant ball of dust floating and it's remarkable what we've been able to accomplish. And the backstory that people don't usually get into is that you have. We had to work with our competitor Planck. We actually, to get the definitive result, we had to beat our telescopic swords into plowshares and work together to really assess, well, this dust, is this synchrotron, is this radio, is this blah, blah, blah. And only in doing so did we have the definitive measurement that actually BICEP 2 is a very effective, very precise dust detector. But that doesn't mean it was a failure, because in many ways it's still the most precise measurement ever done in this field by orders of magnitude compared to other projects that I'm involved with, and it really set the agenda for how science should be accomplished, which is ironically what often happens with Nobel Prize winning experiments. So there is this artificial kind of emphasis on this relatively obscure award, which was never intended to do what it does now, and is really given away by, mostly, 500 white Swedish guys every year, predominantly male. And, how reflective is that of science today versus in 1896 when Alfred Nobel endowed the prize?
And also the fact that it only goes to 3 people is definitely not reflective of how science is done today.
That's exactly what I was just going to say. I don't know. How many people are on BICEP 2? How many people are on the Planck teams?
Yeah, we're talking 49 for BICEP 2. My current experiment, Simon's Observatory, is 245. And, you make the case that it made a lot of sense back in 1896, because that's what scientists were doing. William Röntgen, who won the first Nobel Prize in physics, he was working alone in his lab and he discovered X-rays go through metal. And that won him the Nobel Prize, the very first one. And he didn't even show up to collect it and didn't even care, seem to care. I mean, you can't even imagine that nowadays. Somebody not. And now, so they changed it later on that 3 people could win it. But, that, I think that just made it even more insulting. It would almost be better if they kept it. As Alfred Nobel said in his will, I want it to only go to 1 person. So the committee has changed radically from what Alfred Nobel intended. And the changes have been done in a way to enhance the allure of the prize for the benefit of the prize givers, not the fields in which it's awarded, nor the scientists that might aspire to it and come up short.
So obviously you lost the Nobel Prize on this occasion. Do you see it in the future?
You'll see in the book, I really don't. I kind of went 180 degrees from really seeking this out, wanting to win it as a young graduate student. The year I became a graduate student, a gentleman by the name of Russell Hulse won it, and he was a graduate student when he did the work that won him the Nobel Prize in the 70s. And I just thought it was the coolest thing. I wanted to win it because winners get elevated to this godlike status, and I explore that in the book and why that's bad for science.
Well, that sounds like a great read. It's on my reading list. I will definitely check it out, and we encourage everyone to go check that one out. So thanks again, Brian, for being on. Cheers.
Thank you.
Cheers.
Cheers. I'll toast to you guys with my Klein bottle.
That's great.
Take care, guys. Thank you very much.
Thanks.